I think it should be fine.
Okay.
And then, so you don't, there's not, so it
Yeah.
doesn't go into any speakers.
Yeah.
The parts where we deal with upper administration, which are always ridiculous. So don't have to do that as much. Right, shall we? Yeah.
Okay, so this afternoon, it's a pleasure to welcome Simin to talk about whatever is up on the slide.
Okay, so today I'm going to discuss the results of some recent work that I have been doing with Todd Strohmeyer from NASA. And it is basically about neutron star seismology using accreting millisecond pulsars and low mass Xray binaries. So as you all know, like compact stars are basically the only laboratory for the study of cold ultra-dense matter. And like neutron stars can basically contain different phases of dense matter and exotic forms of matter. For example, they may contain like hyperons or pion or kaon condensed matter inside, or we may have like strange stars. And dynamic properties of neutron stars, such as the temperature evolution or oscillations of neutron stars, can be powerful probes for neutron star interiors. As we all know, like mass and radius of neutron stars are very important to determine the equation of a state of dense matter. But since transport properties and transport properties depend on low energy degrees of freedom, such as, so for example, emissivity or viscosity, conductivity, and etc. And since low energy degrees of freedom are very different in different phases of matter, for example, for quark matter or nuclear matter, these are like quarks or nucleons. So then those properties that depend on low energy degrees of freedom can probe the interior of neutron stars, like the phases that exist inside neutron stars, more efficiently. And some of these, like as I mentioned earlier, like some of these dynamic properties are neutron star oscillations. So neutron stars can support a variety of oscillation modes, like for example, pressure modes or shear modes, gravity modes, inertial modes, and R modes. And these are classified in terms of the restoring forces. For example, for pressure modes, the restoring force is internal pressure fluctuations, and for gravity modes, buoyancy is the restoring force, and for the inertial modes and R modes, Coriolis force is the restoring force. And these modes have different oscillation frequencies. So just to show how these oscillations depend on the interior properties and like phases of dense matter, I will just explain a little bit about R mode oscillations that I have been working on in the last few years. So R modes are non-radial oscillations in neutron stars, and the mode pattern for R modes are co-rotating they are retrograde in the co-rotating frame of the star, and they are prograde in the inertial frame, and therefore they can emit. These are like a quadrupole. For example, M equal 2 R modes are quadrupole, and they can emit positive angular momentum in the form of gravitational waves, and therefore, since they have negative angular momentum in the co-rotating frame, their amplitude can grow as a result of emitting gravitational waves. And they can therefore spin down the star quickly if there is no damping, or if the damping is not high enough. And viscosity, for example, or other kinds of dampings can saturate the R mode amplitude. And therefore, so these like the frequencies of the modes, and also like the damping time scales depends on the interior properties of neutron stars. So the amplitude of an R mode evolves as e to the I omega t, which this is the oscillation frequency of the mode, minus t over tau, and this tau is the damping or growth time scale of the R mode, which is 1 over tau gravitational radiation, like minus 1 over tau gravitational radiation, plus 1 over tau s, which is the shear viscosity time scale, and 1 over tau b, which is bulk viscosity time scale. And if there are other forms of damping, then they will be added like there. And since like here this is the viscosity as a function of temperature for different phases, like this is for quark matter, and these are hadronic matter with direct Urca and hadronic matter with modified Urca process. And if we pick, like, for example, 10 to the 9 Kelvin or 10 to the 8, you can see there is a very large difference, like between 10 to the 24 to 10 to the 28. So the viscosity changes very much. Therefore, the damping time scales for different phases are very different. So if we have a neutron star that has a quark matter core, the damping of these modes in the quark matter core is very different from the damping of the nuclear matter crust or nuclear matter regions.
What controls what controls the width of those?
Oh, these are two, like you mean these two or no?
Yeah, exactly.
So here, like the resonance peak, it depends on like the rate of the reaction. So for example, for direct Urca, like so it depends on the rate of the direct Urca reaction. And when the rate of the process is the same as the oscillations of the star, then you have maximum viscosity. So it is like you get the maximum viscosity when the rate of the equilibration process is the same as the oscillations in like each fluid element. So
Yeah, no, but I'm thinking about width, not the peak. The widths are very different. There are various processes.
Yeah. I think like that is also like let's see. I think it depends on like the like what.
It's not just that the
The
temperature scaling of the reactions.
Yeah,
is
like
different. So in the quark case, you got more, direct reactions, so they got different temperature scaling from the say the
Yeah,
Urca reaction.
exactly.
That's all.
So it is like kind of the phases space for the yeah.
Yeah.
So it is like the weak.
Density?
Yeah, so like these are like for the weak equilibration rates. They have different temperature dependence for like.
Yeah, I'm talking about the density. What densities these chose? Temperature, I see.
Well, this is non-leptonic. What is non-leptonic here?
So it is just like a strange quark to Don quark.
Strangeness.
Yeah, a strangeness. Yeah.
So that's why it has a different temperature
Yeah,
dependence
yeah.
compared to direct Urca.
Yeah, exactly.
Otherwise, they both have T to the 6. right?
Yeah. 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 So and also like so these are like the frequency of the R mode oscillations as a function of the rotation, rotation frequency of the star. And again, like for different processes, this blue one is for a strange quark star, and this red one is for a hadronic star, which is completely made of hadronic matter. And these are for hybrid stars. This is like, for example, medium quark matter core and nuclear matter crust. And you can see when you go to, these are just like the effects from the rotation of the star. And when we increase the rotation rates, the frequency of the R mode, which is in the non-rotating case, it is just 2 over m plus 1, which m is like the YLM, so it is a constant. And so it will change from, this is like in the inertial frame, so it changed from 4-third times omega, so from 4-third to lower values at high rotation rates. And therefore, like, I just wanted to show that the oscillation frequencies of these modes also depends on the phase of dense matter that exists inside the star. So then how can we see, like, how can we probe these oscillation modes, and how can they be, how can we observe these modes if they exist inside the neutron star? One of these, so there are 2 ways that they can modulate the X-rays. For example, these pulsation modes can modulate the temperature distribution across the whole neutron star surface. And in that case, the spin that can be probed is like the inertial frame frequency of the mode. And also they can, these like oscillation modes can perturb the X-ray emitting hotspots on the surface of neutron stars. And in that case, since like the hotspots are fixed, they are believed to be fixed at the surface, then the oscillation frequency that can be detected would be the co-rotating frame frequency of the mode. And the most relevant modes here are quasi-toroidal modes, such as R modes and G modes that have dominant transverse motion. So since like the hotspot is fixed at the surface, if those modes are, they have dominant like transverse components, then they can modulate the shape of the hotspot more than like just the radial components. So here, like in accretion-powered millisecond pulsars show a small amplitude X-ray oscillations, and the period of these oscillations is the same as the spin period of the star, and they are believed to be like due to this X-ray hotspots due to the accretion that are very close to the spin axis of the star, and due to the rotation of the star, they will produce these X-ray modulations at the spin frequency. If like these oscillation modes exist and they can perturb the, so like this one here, the black curve is an unperturbed hotspot at the surface of the star. And then I have shown here like 3 different like perturbed hotspots due to L equal M equal 2 R modes. And this red one is the perturbed hotspot at t equals 0, and this one is green one is at t equal to 1 spin frequency, and blue one is like 2 times the spin frequency, spin period of the star. And you can see like these oscillation modes at the surface can perturb the shape of the hotspot, so they can produce like these, they can be observed in these light curves from the hotspot.
Is temperature small enough that it doesn't affect the oscillation patterns themselves?
So like the, so these oscillation modes can perturb the temperature at like in the whole like surface of the neutron star as well, but the effect on the X-ray emitting hotspots would be larger than just perturbing the temperature in the whole neutron star. But I will explain that one like later also. And so how much they can modulate the X-ray emitting region depends on the amplitude of the R mode. So if the amplitude, or like any oscillation mode. So if they have large amplitude at the surface, then they can modulate the hotspot a lot, like the shape of the hotspot, and they can be observed. So
sorry, can you be confident that in the absence of these modes, your unperturbed spot is really circular?
No, but these are just some. I mean, if we assume a circular hotspot, then this is like how it can change, how you can get the frequency. Because what matters is which frequency, we want to get the frequency, not how much. So
you're not measuring the shape of
no.
the hotspot.
You're measuring the, yeah. Yeah. So then, so as I said, since the hotspot rotates with the star, so it is fixed at the surface, then this modulation frequency seen by a distant observer would be the co-rotating frequency of the mode. So here, this is the normalized Fourier amplitude for the light curves produced by L = M = 2R mode. And this is at 1 is the spin frequency of the star. And this is 2/3 is the frequency of the R mode. And no, this is just the theory, but I will explain the observations later. So actually we observed a very high peak. So then this is the amplitude of these modulations they are proportional to the maximum of the perturbation amplitude or the amplitude of the oscillation modes at the surface.
Okay, so the ones at 2/3 is the R mode.
Yeah.
What is, this is alluding to probably what you're going to talk about later, but what is the one at roughly 4/3?
You mean the small one? Yeah, I'm not sure. This is
do they know what is causing each of those?
No, I did a similar search, but I just got the 2/3 and the harmonics of that one. Yeah, I'm not sure. But this is from Numata and Lee. So.
In their paper, do they understand?
No, I didn't explain. No, just the harmonics. So we did some pulsation search in some of the accreting millisecond pulsars and also in one Superburst from 4U1636. So in these three accreting millisecond Xray pulsars, we found an oscillation mode. We detected an oscillation mode in only this one, and we didn't detect any oscillations in these two. But we recently observed a more significant peak in this Superburst one. So here I will discuss the result of our searches. So for XCJ1751, we searched so this is the light curve from that source during the the discovery outburst. This is from RXT data in 2001. And this is the search in the 2 to 60 kV band from Xray, and from these are in the 5 days that has the highest luminosity during the outburst. And then so we used the orbit models to remove time delays associated with the binary motion. And here then from that light curve we can get the power spectrum. Here you can see this is the power spectrum, and so this is the spin frequency of the star, and we detected an oscillation at about 0.573 times the spin frequency, which is about 249 hertz. And the estimated the significance of this peak is about 1.6 times 10 to the minus 3, which is a little bit better than 3 sigma detection.
So a question about that. I mean, we talked a little bit about this. Looking at that stretch that you have,
yeah.
it certainly appears more significant than that. given the number of peaks you have, must be well, a couple of hundred at least, and stands well above it. So is this a conservative estimate of
Yeah.
significance?
So like this one was, for this one, this is like for the J751, we like, for the number of trials, we put like all of the frequency bins in the ranges that we searched. So this is like a targeted search in the range of frequencies that we expected, like from R modes or G modes. And so it was like e to the minus p over 2 times the number of trials for.
Yeah, so the single trial significance for this is much better.
Yeah, it has like 10 to the minus 11 or something, then times the number of trials, which is a lot. So it will give like 10 to the minus 3 because we put like so the number of trials, we use the total number of frequency bins that we searched, which is like a lot. And so the employed modulation amplitude for this peak would be about like 7 times 10 to the minus 4, which is like if we assume this is, and this is a coherent signal over the 5 days range of the detection. And if we assume like, so then the amplitude of the mode should be about like 10 to the minus 4 or 10 to the minus 3 at the surface to get this amplitude, this modulation. And some of the possible mode identifications just based on the frequency of the mode would be like surface G modes or inertial modes or core R modes. Because as I mentioned earlier, for m equal to R modes, the co-rotating frequency is about like 2/3 times the spin frequency, which is about 0.66 times the spin frequency. And this one, the frequency was about 0.57, which is a little bit lower than R mode, but I will explain later how this can be an R mode possibly. But there are some other discussions. First, I will explain the other source that we searched, and then I will explain like the mode identifications. So the second source that we found an oscillation mode in it was 4U1636, and we searched the superburst. So superbursts are rare and energetic X-ray flares that from low mass X-ray binaries that are caused by unstable thermonuclear burning of carbon-rich layer that is produced from ashes of normal type 1 X-ray burst. And since like there is so this like superburst, during the superburst we get a very high luminosity and also a long duration. So the number of counts in the X-ray detector is a lot, is very high. And also we have some information about the orbital constraints that were derived from the 500. So the frequency of this pulsar is about 582 hertz. And so therefore we can use the orbit models to remove like some of the orbital, like the phase delays due to orbital motion. And also the thermonuclear burning can provide a mechanism for excitations of these modes at the surface of neutron star. So we searched.
So sorry, a question
Yeah.
about that. So in terms of the 5.82 hertz pulsations and looking for coherent R modes, of course, in shorter bursts, you do have a drift in the frequency, which is not due to orbit, it's due to some intrinsic drift. You might be about to say, but how much of an intrinsic drift in the thermonuclear burst oscillation frequency could you tolerate? Would it mess up your coherent search for R modes? Does it have to be truly exactly constant in the rest frame of the neutron star, or could there be a part in 100 type change without affecting your search?
Yeah, like so I don't have, I think, a plot of that one, but we fitted like sinusoidal. No, I think if like you have a little bit like drift, it doesn't change. So if you have the best orbit model and remove the phase delays from the orbital motion, then you can get the coherent, like you can see the signal. So it doesn't.
I mean, I guess if the oscillation was tracking the drift, then it would become a quasi-periodic. It would get some width. But if it's not, then you would still get the same old peak frequency. Right?
Yeah, I guess that's right. I mean, to some extent, would it be the case that any intrinsic, so you're locking onto the burst oscillation.
Yeah.
Any intrinsic drift in that, would it tend to decrease the significance of any other feature that you're looking for? So if your frequency model isn't quite right,
Yeah.
is that,
It's,
would it decrease the significance of something that has truly?
Yeah, maybe like so. If we change the orbit parameters, then the significance also, if it is not the true like orbital model, then the
I mean, would it turn a periodic oscillation into a QPO? And therefore, since when you search for a QPO, you have to have extra parameters, would that eventually decrease the significance?
Yeah, maybe you're right. Yeah.
It all depends on how you're doing the search.
Yeah.
So you take a very sharp unresolved line in Fourier space and you broaden it.
Yeah.
Yeah.
You preserve the power in that line. That means you depress the peak.
Yes.
So it's easier to hide it in the noise.
Yes.
So depending on how much you broaden it, okay, it's almost a linear problem.
Yeah.
The more you broaden it, the more you reduce the peak, and then you go through the probability exercise, and you find that the peak is lower than your criteria.
Okay. So if that's the right picture, then I guess what this is saying is that the significance you find is if anything possibly a lower limit, but it's not an overestimated significance.
Right.
Yeah.
But, I mean, surely it's, okay, it depends on how you're doing the search, right? But surely if you do it sort of, if you ask yourself, well, do I have evidence for extra power over a narrow frequency band, then the only thing that matters is the total amount of power, right? If it's washed out over a couple of bins, it shouldn't actually hurt you any.
But I don't think
If
that's
you're
true.
well above the detection limit, then that's right.
But in terms of the absolute significance, I don't think that's true, because if you're allowing yourself to have something that extends over more than one frequency band, you do have an extra parameter in your model that you're using to look for the power excess.
You mean the width?
Yes.
Yes, that's right. But you can mitigate it somewhat. If you have a suspicion that that's what's going on, you can break up your time series into smaller pieces and do the search separately and then align them. And
That's right.
Yeah,
And
but-
so
Oh, you're
then-
So
linear,
this
so the
is like-
temperature here in search is not as sensitive this way. Okay.
Yeah.
Yeah.
Okay, so here this is the light here from the 8,000 second during the like Superburst in 2001, and then like the orbital frequency model that we use to correct the event times is like the red one. So you can see like these are the frequency. So like from this light here, we produce this power spectrum. And you can see here, like this is the pulsar frequency at 1. And this is the oscillation, the mode that we detected at 1.43 times the spin frequency. And the estimated significance of this peak is about 2.5 times 10 to the minus 4. And this is like conservative significance. So we use like e to the minus, so the power is about 49.3. And the significance of the peak is like e to the minus 49.3 over 2 times the number of trials. And for the number of trials, we use 4 times the total number of frequency bins in the ranges that we searched. And this 4 is because of the 4 energy ranges that we searched for our that we made this power spectrum over.
Sorry, for non-experts,
Yeah.
if you could explain. The significance seems very small to me. Should I be worried, or are you happy, or what is the story? 10 to the minus 4.
Think of that as a chance probability. So the inverse of that is the significance.
Okay.
This is pulsar too.
Ye-
One minus this quantity is the significance of
Is
mean.
it
Oh,
one
okay.
minus or is it the inverse?
No, one minus.
One minus, okay.
So it's pretty good.
Yeah, it's
Smaller is better.
Okay.
Smaller
Because you
is-
know, you say significant, you said, if you give me a number that is 10 to the minus 4, I'm not terribly impressed with it.
Even if the estimate that is around
Yeah, 1 minus that number, okay.
Yeah, 1 minus that.
I can relax.
This is also quoted in the literature.
So these episodes last for how long? Do you see these lines disappear also later in the data?
So we searched over 8,000 seconds of the superburst, the highest amount of power that we had, and so that is a coherent signal. So this is a coherent signal over the whole 8,000 seconds. So it didn't change, the frequency didn't change over time. But
The superburst lasts 40
it lasts a little bit longer, but we used only the portion that had the highest rate, the photon rate.
Continuously, and you do see it suddenly, the oscillation suddenly disappear, or?
No, the oscillation during the whole 8,000 seconds is coherent.
Yeah,
So there's
but you said that the superburst lasts longer than that.
yeah. So we didn't include in the first search we didn't include the whole thing, but then later we searched over that portion. But since the amount of photons emitted during the later times is lower, you cannot see the oscillation.
So if you could go back to your light curve,
Yeah.
you had an Earth occultation
Yeah.
there, and so which portions of the burst were?
So we searched the whole thing. This is the whole thing that we searched, this 8,000 seconds. There are more data later, but then the count rate is lower, so we cannot search we cannot detect any oscillations during that portion.
And when you analyze two segments independently, do you find that the phase is as expected when you pick up after?
Yeah.
Why is there a break in the black hole?
Because of the Earth, so
It's a near Earth orbit, so the Earth calls the source,
yeah.
or was.
You can't see.
May it rest in peace.
Okay, you guys understand, I'm happy.
So it actually passed it, it eclipse the source side.
Okay, so this signal, as I said, it is at 1.43 times the spin frequency. And here, in the previous case, the signal was at 0.57 times the spin frequency. And this one is at 1.43. So for an accreting millisecond X-ray pulsar, we expected to observe the oscillations in the co-rotating frame because we thought these oscillations are perturbing the X-ray emitting hotspot, which is fixed at the surface. But for a superburst, since the whole surface is emitting at very so then we expect to see the inertial frame frequency because it will these oscillation modes perturb the temperature, modulate the temperature over the whole surface. And what we detect is the inertial mode frequency. And if we have the inertial mode frequency, so the frequency of the mode in the inertial frame is related to the frequency in the co-rotating frame by this formula. So M is the spherical harmonic constant, and omega is the rotation frequency of the neutron star. And here, for example, if we have an M equal 2 mode, either R mode or G mode, then the co-rotating frame frequency is related to the inertial frame frequency by like 2 minus omega I. So if I just like divide all of these by omega, then omega I over the rotation frequency of the mode is just m minus omega r over capital Omega. And therefore, like for this mode in the superburst, we will get a co-rotating frame frequency which is 0.56, which is very close to the ratio that we found in the accreting millisecond pulsar. So this suggests that these two modes can be related to each other. So they might be basically like the same oscillation mode that we detect in both of these. Yeah.
Is there any error estimate on these two spin frequencies? Like the error can be possible, error can be in the last significant incident?
So this is like the spin frequency is measured like very accurately for these like neutron stars. And then like these are measured from like these are like a coherent signal over a very narrow band. So since like the frequency is observed very, so there's a very significant measurement for the spin frequency, then the frequency of the modes would be also significant.
I was wondering when you said that these two, next slide, these two spin frequency are
Okay.
more or less equal.
Yeah, so like they are about 1%, 1 or 2% difference between these two. But
Yeah. Is there any possible way of accounting for this frequency?
so these are just like from observations. So depending on these are in two different sources. So depending on the condition, like at the surface of these modes and like which kind of mode we are observing, if it is an R mode or G mode, it may depend on the accretion rate or temperature or other things at the surface. So the frequency can actually change.
I guess another way of asking that question is, what is the limiting factor that determines the error in this measurement? Is it the model that you're using, or is it more observational?
You mean like the error in?
Yeah.
What is the cause of the most error?
Yeah. The estimate.
Well, you have 3,000 seconds of data, right?
Yeah, so the
so,
graph is-
so your
Yeah, you are-
graph is 1 over 3,000 seconds.
Yeah, but so
right?
I'm guessing
You
that is not
you can do a
because-
little part of that, but not too small of a part.
But I mean, the difference between those two is two different sources. If it's the R mode, it could just be the mass.
Yeah,
Could, I mean, R mode has mass radius scaling.
yeah.
That
Like
could-
or like for G mode, like temperature or accretion rates. Yeah.
No, I guess the question is very valid because you give the number to 5 significant figures there.
Oh, these are just from observations, and like since we know the rotation rate, like rotation frequency very accurately, we can get the oscillation frequency from observations very accurately. But then the
Yeah, but then
relevant,
you try to compare it.
Yeah.
So many significant figures with this.
I mean, it's just like,
Then
pulsars
you
can time it to even better accuracy than
No,
that.
Yeah.
No, that's exactly the reason why the question becomes significant. Because you can measure the pulsar spin frequencies very accurately, then I would have said that, well, if there are so many digits that are very significant, then my inference for the co-rotating frequency is also very significant. A comparison of 0.56454 with 0.572776 would tell me that, it's not a good model. It's not a good.
but these are two different systems. Like one of them is in a superburst, and the other one is an accreting millisecond pulsar. So like one of them, we are assuming that this is like perturbation of the hottest spot, Xray emitting hottest spot. In the other one, it is like during the superburst, so like the temperature is very high and.
Exactly,
Yeah,
so
but-
it's
but
exactly, but that's why it's question becomes.
How much you can allow this range from the physical model of the temperature variation?
Actually, you can change, I mean, just like from the theoretical models, you can get very different, like depending on the mass and radius and
Exactly.
temperature, you can get many.
So which of the many things that he mentioned, Wing mentioned, causes, differences that can be attributed, and by how much is the real question.
I tell you,
Okay.
so my worry with this is that they're too close.
Yeah.
Because
if
if
it
you-
was me, I would have called it 0.57, 0.57.
No, because
to government accuracy.
because really
declare
this-
victory.
the variation with the mass radius is quite significant.
Yeah.
Okay.
Yeah, I have actually
So-
another.
I guess
If
Yeah.
you associate that with the R mode, then you are determining the mass to, if you know the radius, to that accuracy. That's amazing, right?
Yeah, yeah.
But
Or if you know the mass, you're determining the radius to that
Yes.
direction.
Yes.
There you go. Now,
But
he's
so
not
the fact
nuclear
that,
physics.
again, if it's the R mode, the fact that those two are so similar means that their masses are that close. Those in these two independent systems, neutron stars, have masses that are that close to each other. But it's not the R mode.
Yeah.
Well,
Yeah.
So I was going to ask that question.
Yeah. So I will discuss. So like some of the identifications are like G-modes or it can be like inertial mode or core R mode, just like based on the frequency. And so like G modes or gravity modes, they have a frequency which is between 2 to 30 hertz in the non-rotating limit, but due to the rotation, they will be modified and they can actually have very high frequency, like have higher frequencies when there is a high spin rate. And this is like the mode that we detected in the accreting millisecond pulsar, that like in the co-rotating frame one, is consistent with L equal M equal 1 and L equal 2 M equal 1 thermal G modes. And so like there is a problem with G modes, and that is at high spin rate, spin frequencies, they will be squeezed like near the equator. So like if the hottest spot is near the spin axis, then it would be difficult to explain that by a modulation due to G modes, because they will be more close to the equator than the spin axis. But this won't be a problem for the superburst, since like superburst, it is emitting, like the whole surface is emitting. So if like those two are not the same mode, then like the superburst one can be a G mode basically. But so then the frequency, as I said, like is consistent with the R mode. So the frequency is actually lower than non-rotating limit of the R mode, which is 2/3 times the spin frequency. And if we consider like the influence of a solid cross and like avoided crossing between R modes and the torsional modes, that would push the frequency of the R mode to lower values than 2/3 times the spin frequency. But in a recent paper, Niels and Wayne and Jones, they showed that like gravitational, so the relativistic effects like gravitational redshift and frame dragging, they also tend to lower the rotational frequency of the R mode. And like based on these like just relativistic effects, this oscillation frequency can be in principle consistent with an R mode with plausible mass and radii for neutron stars. But there is another problem with R mode, and that is like the spin down. Like if the amplitude of the R mode is high enough that it can modulate the hottest spot at the surface a lot, like or like based on this paper by Numata and Lee, this modulation amplitude is about amplitude of the R mode divided by 2. So in this case, the amplitude of the R mode would be about 10 to the minus 3 in our case, because the modulation amplitude was about 7 times 10 to the minus 4. And an amplitude for the R mode, which is about 10 to the minus 3, would spin down the star very quickly. And the amount of spin down during that 5 days period would be even higher than the spin up due to accretion. which is like not consistent with the observations. So therefore, like although the frequency of the mode is consistent with an R mode, but the spin done is not, like the spin evolution of the star is not consistent with the spin done due to an R mode. But there was another paper recently by Lee, and he argued that there is a strong amplification of the amplitude between the fluid core and the surface fluid or the ocean. So if there is a solid crust in the neutron star, then Lee showed that the amplitude in the core can be about 100 times less than the amplitude at the surface. So in that case, like the R modes can have very large amplitude at the surface, and they can modulate the hottest spot at the surface, but the amplitude in the core can be like 100 times lower. And since like most of the gravitational emission is due to the core, therefore this can lower this can decrease the problem with the spin down.
So what's the limit on alpha core based on the Petruno and Lott study?
So like based on that study and also the one that we did like with Todd, we got about 10 to the minus 6 to 10 to the minus 8. And here we have 10 to the minus 3. So if like with that factor of 100, it would be like 10 to the minus 5. So it is still like larger than the those limits, but it is. So like if in this case, like the R modes are emitted only like during the, so if they are excited only during the burst and like during the outburst, or for example for the superburst only like during that 5 days or like 8,000 seconds, then that may not be. So it depends like if the R modes are excited over a longer time or they are only excited during that period that we are observing.
Are there mechanisms for only exciting it during bursts? I thought the mechanism was basically acting continuously.
No, so like if they are excited due to like thermonuclear bursts, then
is that plausible?
Yeah, like so it also depends on like what can saturate the modes and like what is the damping. So we don't know exactly like what is the damping mechanism or saturation.
So I think that, well, there's a discrepancy because I mean, again with the instability, because it's unstable, you only need to kick it a little bit, and it's unstable, it'll grow. But the problem is that the observed amplitude, even at a factor of 500 less, as you would expect that R mode to spin down the star while it's active. But for 1751, it's actually spinning up, not spinning down. That's a huge discrepancy.
But,
I mean, 1751 is accreting, so you can certainly think about it spinning up.
Yes, but if it's has an R mode active at 10 to the minus 5, that's strong enough to be spinning it down.
Based on what assumptions about the magnetic field of the star? I mean, if the accretion is coming inside co-rotation, that's when it's going to spin up. Are you saying that at the approximately known accretion rate, it doesn't matter where the co-rotation point is, that it'll still be spinning down due to the R mode of that amplitude?
If you take the standard accretion model for the expected magnetic field, there is no way this is 3 or 4 orders of magnitude too strong.
Wow.
If you can fiddle with the accretion torque, if we play with this for a moment, we say, let's suppose, as we probably can all agree, we don't know the accretion torque exactly.
You know it's at 3 or 4 orders of magnitude.
Well, exactly. So I think, but you would have to give that sort of difference to it. And I don't think that's not plausible.
Well, yeah, second that. Okay.
There is, of course, the other caveat, which is those back of the envelope little equations for how the stars should evolve under the influence of an instability, which are really back of the envelope. They could be completely wrong in the sense that they're based on average quantities that don't weigh in how the transport goes in through the star and all that stuff, all the dirty stuff, right? that it could be that it's not the right model to compare to.
Yeah.
In this 1636 source, during the superburst, is it spinning up or spinning down?
I don't think.
I don't think it has been up there yet. There is no long-term like observations for
during the burst. I mean, you're tracking the spin frequency of.
I don't think that is that's precise to.
Okay, in the superburst, you're not tracking because you're not tracking the spin frequency there.
You are tracking the spin frequency, but the change in the spin frequency during that 8,000 second period is absolutely negligible. You typically.
Yeah. It was like I showed like.
Or at least several weeks.
Yeah, like
But
these are like the,
But doesn't that then already place a constraint on the R mode? Because you don't want to have it exactly equaling out the accretion and the R mode exactly equaling out. So that would tell me that it's just not. There's nothing to do there. If it's not changing, then the R mode amplitude can't be above some value.
I guess. I mean, so along with that question, part of the difficulty may be that there's a degeneracy here because you're fitting the orbital evolution based on the spin frequency you're inferring from the superburst.
mhm.
So if there were some sort of R mode contribution, that would be swallowed up in your fit, wouldn't it?
Yeah.
But I guess you guys are right that there's some limit. I guess the question was, is it useful? Right. I mean, it's a really short amount of time to see a spin frequency change.
Yeah.
I need some lesson here. Maybe you just can help. He's the Pope of Armors, I guess.
This is not a religion,
It is.
It might be.
So I'm trying to understand. Once excited, the armor, okay? I'm asking a very gross question here in terms of the time scale over which an observation can reveal that there is an armor. What is that time scale? Because
So I think that
you're talking about superburst time scales, and there could be another source which could be.
Oh, but that
The
was
excitation could have been because.
coherent
Yeah,
over
but I
6 days.
Yeah. What's the time scale? over
Well, I
which-
think it depends entirely on what scenario you're looking at. If you want an R mode with the known damping mechanisms that we've got to live for the 6 days in the first observation, then it has to be continually driven by something.
Yeah.
It could be unstable, or it has to be fed, right, or pumped in some way, which, if it's gravitational wave stable, which I would have thought it should be, then we don't know how that works. And in this case, 6,000 seconds, I think is short enough that it should be okay, if it's stable, right? If it's a gravitational wave unstable, then the amplitude should grow.
Yeah.
And funny enough, roughly up to the amplitude of the first case, right?
Yeah.
So that also works, but then you should see quite a dramatic spin down, which you don't see, because that system spins up during the Xray burst. So I don't know. The religion is dead. God is dead.
I mean, if you're kind of realizing inconsistency, that's exactly the reason why we're thinking that it's not an R mode, because there's this inconsistency.
Yeah.
But yeah, so we tried very hard to make this work.
Yes.
Because so we've never looked at stable modes that are pumped by some, but you always pay that angular momentum penalty. Because you put it into gravitational waves no matter what you do, and that will be radiated away. And that penalty is always there, as long as those simple equations are valid.
Mhm.
And so if you wanted to, I mean, suppose you kept on seeing this, and suppose it fits a little bit too nicely, then you would have to ask, where is the gap in our model? And then it would have to be there.
Mm.
Right? Or in the accretion, but as you said, that's just not uncertain to that degree. Right? So, that's my feeling.
Yeah. So, yeah, so like basically like based on just one oscillation mode in one or two neutron stars, we cannot decide which mode it is, like if it is an R mode or G mode. If there were more oscillations, then we could see, like we could compare the spacing between frequencies, and then it would be easier to determine, like, I mean, it is not necessarily like 100%, but it is like, it would be easier to say if it is on this G mode or R mode based on like different, like several oscillation frequencies. But the problem is, like in all of these, we have just like one oscillation mode in both like two different cases. And so like with some like future X-ray satellites, like if LOFT would be a perfect X-ray satellite because it has a larger like collecting area, and like we need more photons to be able to see these small oscillations. But even so, it would be able to see like about amplitudes of the order of 10 to the minus 5 with LOFT. But with NICER, it has a smaller effective area than RXC. But if we can detect, so this NICER will be in orbit like in 2016, at the end of 2016. So it is an approved NASA mission. And with NICER, if we can see detect a brighter source or over a longer observation time, then we might be able to do similar searches in new sources. And also, like we can search for oscillation modes in rotation-powered pulsars, since they have similar like hotspots at the surface. So just in conclusion, like the detection of global neutron star oscillation modes will open a new window into the neutron star interiors, because the oscillation modes and time scales of these damping or growth of these modes depends on the phases of dense matter and the structure of neutron stars. And even small mode amplitudes may influence the X-ray flux to measurable levels. And we need to confirm the detection of this candidate in J1751, maybe like with future observations. And there are additional sources such as SAXJ1808 that has more data. So we are currently like searching other accreting millisecond pulsars for these oscillations. And then we need more like theoretical models for G modes and R modes, like in more like physical models to see like how the frequencies changes and if they are consistent with the observed oscillation modes. Okay, thank you.
(1636), in addition to its superburst, has a ton of normal X-ray bursts. Have you been studying those for this
We
reason?
haven't yet, but yeah, we will.
Especially since you now have a
But
very
they are
precise prediction of the frequency. You wouldn't pay the enormous N trials penalty for those.
Mm-hmm.
Can you remind me what the spin frequency of 1636 is?
How do you
500 or
580.
yeah. Oops. Sorry.
there? Oh,
You just said it.
but
Yeah,
Yeah, 5.8.
were you going to say that there would be some special challenge in looking at those, or?
No, I think like during the normal bursts, I'm not sure like how long we have data for the normal bursts. I think like there wasn't a long duration.
No, there's not a long duration. So the total amount of data, total amount of counts you have from the single superburst exceeds that of all of the other bursts combined by maybe a factor of 10 or 20. But the fact that you're only going to have to look at very
narrow
frequency
frequency,
range.
yeah.
So you wouldn't require that there be phase coherence, because the intervals between the bursts are sufficient, you probably lose that. But it seems like a worthy check. So regardless of what this is, you might end up with a significantly higher significance, all things considered.
Yeah.
You mentioned that so if there is a solid crust, then this ratio is lower, and in the relativistic effect, it is also lower. So this relativistic effect is estimated to include also the solid crust, or if we have a solid crust and
no, they did, like for the relativistic effects, they didn't consider the effect of crust, and
so how much would it change if you put both?
I mean, there are a lot of uncertainties in like all of these. So like based on the mass and radius and which like equation of a state you use, you can change the frequency a lot. So
there are lots of flexibility.
Yeah, exactly.
More than the
yeah, exactly.
I think this may actually be mostly a question for Niels, but I'm trying to understand your earlier comment that there's a lot of uncertainty in the predictions for the amount of angular momentum lost if you assume this is a particular kind of mode. So can you explain that? I would have thought that once, okay, if you make an assumption that it's an R mode, right, and you assume a particular amplitude, right, then surely, okay, you can model all of the fluctuations in the mass multiple moments and make a straightforward prediction. So what could go wrong there by several orders of magnitude?
I don't think, well, what can go wrong there is not several orders of magnitude, but what could go wrong is your inference as to how the different viscosity mechanisms affect this mode. That what goes into this amplitude evolution equation. It's like a body average, saying everything just averaged to one number, right? And that could go wrong. It could be that the communication through the star as to how the spin changes, for example, how you spin the star down is not a solid body effect, right? It could be that the mode actually drives you into differential rotation in some shape or form, and you see something else, right? So it's not. I think you're right. Once you put a certain amount of angular momentum in, and you calculate multiple moments, you know how much you're going to radiate. That's clean, relatively clean. But here we're asking how much of the angular momentum goes into, is destroyed by viscosity compared to gravitational waves. If you change that balance by some argument, then the spin down might be different. That's all.
Is it possible to establish upper limits or lower limits? No-go theorems. It can't be this much, and it cannot be this or about this. Then they may be helpful.
Yeah. Well, I think this is interesting anyway, because you can start asking as you said, the two numbers are very close. That suggests it might be the same kind of thing, right? But maybe when you look at how close they actually are for two stars spinning at different rates, there's a difference of 130 hertz or something in the spin rates, or more, 150. That's maybe enough that rotational corrections to the R mode would say these two are actually too close, right? You said the G modes, yes, but you can look at the G mode spectrum also with the GR corrections, the redshifts and so on, which has been done to some extent, but not for realistic sort of ocean equations of state, right?
Yeah.
But that one could do, and then you can say, well, what actually lies in this frequency range? That I think you can start doing.
I mean, in the 1636 one, the frequency in hertz is almost, it's like 900 hertz. I think that's pretty high for a G mode if it's a G mode.
Well, that was my feeling, but I can't remember. We did this, but not, as I said, not for a real equation of state. We did that traditional approximation where you just, the one you showed essentially, but in full GR.
Yeah.
But I can't remember, so I'll need to look that up.
So the way I understand is that the R mode analysis is more difficult than the other modes. So the other modes could be controlled in the sense of the use of a realistic state, and
that's right.
Put a band.
But this could also be an R mode that only lives in the ocean.
Yep.
Right. So it's basically got a different boundary condition at the cross. It only lives in the upper 100 meters or whatever, and that's it. and then it doesn't radiate any gravitational waves at all, and then that's not a problem. And the frequency, I think, is going to be pretty much the same.
Yeah.
So I think that could work. But again, that's
Yeah.
Should believe that the hormones are restricted to this ocean, or is there an argument saying that it should?
I think it's part of we'd like it to be the core ones because it's gravitational.
we like gravitational waves. That's it.
That's why it's in the armors.
But there have been, like there have been work on G modes in the ocean. There are same sort of work on R modes in the ocean, and they basically truncate across.
So maybe to rephrase in another way. So what are the conditions you can infer from? If you assume that it's really an ocean R modes, what are the conditions you have to impose? I mean, boundary condition, whatever, to satisfy all the observational constraints, or that would be interesting.
I think the bottom line is you need to do this calculation. Go back to this. I mean, when people did these ocean modes, it was for a different, with a different motivation. They were looking at variabilities in other neutron stars, and they was trying to see if they could get a certain ballpark number. Now we're looking at fast spin, but if we had a proper ocean model, which I guess we can squeeze out of Andrew Cumming next week, then this can be done. That's not, it's not a problem. It's just there was no motivation for doing it, right? The gravitational wave motivation is different, right? Because then you can fool Sukanta, he's going to go look for this.
Do you have any observational constraints on the variations of the amplitude of this mode over the course of the burst?
We only searched, we divided the burst to two parts, and there wasn't any difference on the amplitude in those two parts. But we didn't search how, in a smaller segment.
Okay, but even that's already, the fact that there's no difference is already telling you something, right? It's sort of saying that you are in some stable regime.
Yeah. Yeah.
The amplitude of the two part at the absolute amplitude or the fractional amplitude? The two part that you compared, which are equal, the absolute amplitude of the oscillation, or the fractional amplitude?
No, they are so it is not actually the amplitude of the R mode. So if we believe that this Numata and Lille's model is correct for, so this is this is a theoretical model. So how this amplitude, the normalized. So I was just talking about the Fourier amplitude of the signal, but not so then you can connect that Fourier amplitude to the amplitude of the mode by theoretical models. So the Fourier amplitude of the mode didn't change in those two parts.
But it's the fractional amplitude.
Fractional, yeah.
So then what is the real amplitude of the, because what you can say really is what the real amplitude of the surface, so how much is the displacement at the surface, what is the deformation of the surface. So
yeah, so
how large is this in meters or kilometers or whatever you use?
So if alpha is about 10 to the minus 3 or yeah. So I think the displacement, I don't remember exactly, but it is something about 0.3 times alpha, or the displacement over the radius of the, so delta R, so this, the maximum displacement over the radius of the star is about 0.3 times alpha, something like that. So for an alpha about 10 to the minus 3, it would be about 10 to the minus 4 times radius, the maximum displacement at the surface.
Is an individual pulse result or not in these observations? Do you see the shape of the pulse?
You mean like just like for the arm? Sorry, yeah.
No. Just you see X-ray pulses
Yeah.
from the period.
Yeah.
Are these pulses resolved? I mean, do you see the shape of the pulse? Like in radio, for radio pulsars, you see the shape.
So these ones are consistent.
No,
sinusoids?
like yeah.
Well, I mean, changes in the pulse shape might indicate that there is some precession in this object. I was wondering whether these are not oscillations but precession.
So, I mean, you mean the ones at the spin period or the ones at the mystery period?
Accreting millisecond pulse. Do they precess?
I thought that in this case and the other cases, the pulse shape is consistent, being constant over the period of observation. This 1751 was active for a few weeks.
Yeah. Not few. 1751. That was like our oscillations was in 6 days, but there are more data over longer period.
It dropped in flux after 6 days.
Yeah.
Dramatically.
You happy? Right, let's
We can do it tomorrow.
Okay. So normally we carry on with the discussion now, but because we've got time to slot tomorrow afternoon for discussion, which is still open, maybe we should just break, do some work, whatever, chat to each other, and then after Cole's talk, we can start a discussion that summarizes and brings all the issues together tomorrow afternoon instead. Does that make sense? Excellent. Let's do it. Yeah, you have to push.